So we have this periodic table with all of these different elements. Where do these all come from? How do they get made? What is happening? Well, really where a lot of this has to happen is in the center of stars. And the reason for that, where this all happens for the most part, is because you need a tremendous amount of energy and pressure and heat in order to kind of glue these different protons together. So remember the periodic table, each of those different boxes represents a different number of protons and different number of neutrons in there that is going to give it a certain mass, right? If we want to add another proton, it's not simple as just kind of pushing them together. So it requires a tremendous amount of heat and energy there. And then we kind of get stuck after we get to the point of iron, for example. That is kind of the ending point where we don't have enough energy and pressure until we get what's called a supernova. The iron is so dense it ends up collapsing on itself, and then that causes a shock wave outwards and enough energy and pressure to create the rest of the elements on the periodic table. So you've watched these other videos that describe this process, but there's also this idea that with the Big Bang theory is that essentially 14 billion years ago there was some type of explosion, there was singularity. So everything that existed on Earth was within one end of a pin, essentially. And there was a sudden explosion and the release of extreme temperature and pressure and heat and density. And as that Big Bang cooled, we generated quarks and other subatomic particles that were able to condense and come together. So the quarks came together, and after about 1 second, protons and neutrons were developed and formed. And then after cooling, the electrons were able to add on and form the different compounds. So this is kind of that time frame as it expanded out into the universe. The cooling allowed these things to condense. So if it's kind of interesting, we were talking about you have to have enough energy and pressure to get these things to come together. But at the same time, if there's too much energy, then they move around too much and they won't settle in on each other. So you have to have it's like that Goldilocks idea. You have to have just the right pressure and the right temperature. So after about 3 minutes of this expansion and the cooling, then we actually had nucleosynthesis, which means that those protons were joining together to form larger elements like lithium and helium. And then again, the further cooling happened. The universe was about 91% hydrogen, 8% helium, 1% other light atoms. But then the uneven distribution of this allowed the formation of different stars and galaxies. And over time, those small atoms combined and glued onto each other and then created pressure at the centers of these larger groups that ended up turning into stars once the pressure became high enough and the pressure and temperatures went very high. So these then heavier elements combined and formed until eventually, again, the supernova that we talked about earlier could happen. So that's kind of the thought, that's the theory as to how the beginning of the universe occurred. There's still not much known about, why the Big Bang happened or how exactly what was happening before the Big Bang. There's not much information about that, however. Now that we have an understanding of maybe how these different elements came to be, I want to talk about some of the ways that we study them and our understanding of them and other things that are on the periodic table that are going to be helpful for us to recognize and know and be able to use. I'm not going to ask you to memorize the periodic table of elements, but throughout this term, I am going to ask you to utilize that information and understand what it means and how to use it. So in the 1800s, when some of the periodic table elements were being put together, at that time we weren't able to determine the mass of an atom. The instrumentation was not sensitive enough. It wasn't good enough to do this. So instead, scientists examined what was called mass ratios, and they used carbon as the reference. Remember, we talked about in the measurement section that you have to have something to compare to. So carbon was selected because it's the most common, most abundant isotope of carbon, and all the atomic masses of all the other elements, it allowed it to be whole numbers. So we knew that the lightest element was hydrogen, and we made it an atomic mass unit of 1. And carbon was the 12th heaviest one, and it ended up being 12 times the size of hydrogen, and that's why we were able to use this as a reference point. So it allows all of the elements on the periodic table to be whole numbers, and it's really based off of those differences in the number of protons and neutrons within that element. This is how the atomic mass scale was developed because of this inability to look at a specific proton, for example, and get the mass of that. So they looked at this atomic mass units. It can be defined as a U or AMU, or atomic mass units. So all atomic masses are whole numbers. There aren't any decimal points or anything that go after it. It's just a whole number. And again, the lightest element is hydrogen. It has the atomic mass unit of 1. So hydrogen fluoride, HF, they knew that in this compound, if you could separate out the elements, that fluoride was 19 times heavier than hydrogen. So then they could define fluorine as with an atomic mass unit of 19. So this is how this was done. So we're going to talk about atomic notation next. When we're looking at atomic notation, we will have the periodic table symbol, right? So this is an X. There's no X element. But if it's a hydrogen, it's H. If it's carbon, it's C, right? So this is just a generic saving spot for that symbol. So one of the first numbers that we're going to look at is this Z value down below. It's always shown to the lower left of that atomic symbol. So this tells us the number of protons that atom has in the nucleus. And it's unique. Remember, that's what defines an element, the number of protons in there. So it's going to be unique. These X and Z, those terms are always going to match. If you change the value of Z, then the value of X has to change. These two go hand in hand. They have to be always the same number, goes with the same symbol. The mass number, on the other hand, up here on the top, that tells us the number of protons plus the number of neutrons. Now, the number of neutrons doesn't change the chemical characteristics of that element. It just changes the mass of it. Remember, neutrons have no charge, and therefore they're not going to change how the electrons come and fly around the element in any way. So they don't change the chemical characteristics. So to determine A, you have to take Z and then add the number of neutrons. And so again, also something to think about, the number of electrons, if it's a neutral element, those number of protons are going to equal the number of electrons. Now, if we have changes in the number of electrons, that'll be reported out here. So if it's a negative value, we've added electrons. If it's a positive value up here, we lost electrons. So something to think about with atomic notation, here's a term that I want to introduce to you. It's called an isotope. And isotopes are different numbers of neutrons within an element. So let's look at some difference. So you have different number of neutrons. It's an isotope. All right, so the atomic symbols, here we have the periodic table symbol. we have the number of protons and then the atomic mass. So let's look at an example here. So what's the atomic symbol for helium? Helium has 2 electrons, 2 neutrons, and 2 protons. So the Z is 2, the A is 4, and this would be the kind of the atomic notation. Helium is the symbol for that element. It has 2 protons, and its mass in this formation with 2 neutrons would be 4 because we're adding the 2 plus 2. We're just giving the full mass there. Okay, so thinking about the atomic element representation, what is the correct answer below? So if we're thinking between the atomic number or the atomic mass, which cannot be smaller than the other and why? So this, of course, if we are looking at these elements, if we have an element X, remember this value Z is the number of protons, and the value A is the number of protons plus neutrons. So the number that cannot be smaller is A because we're adding both of those elements together. Maybe you have 0 neutrons. It could be the same value, but it could never be less than Z. So one thing you might notice when you're looking at different periodic tables, you might notice that there is on that periodic table information about the atomic mass. And so the atomic number, again, this would be, we're looking at, if we're looking at a single atom. But what happens in real life is you have a group of atoms, and they might have differences in how many protons and neutrons are there, right? The number of protons for a specific element like hydrogen, right? The atomic number here is always going to be 1. For lithium, that's always going to be 3. Boron's always 5. Now this A number can change, and it depends on the number of neutrons that fused within that atom. And so we have averages typically that are shown on the periodic table. So the average atomic mass for hydrogen is 1.00794. Now this is, and this last number is estimated. Now this means that some hydrogen atoms have a neutron and then some don't. So there are different isotopes of hydrogen where you might have a proton and a neutron. Sometimes it's just a proton. And there are intervals given here, usually the highs and lows averages. And those tell you, the interval basically gives you varying differences. So now it depends on what part of Earth you're on. If you're in the United States, or if you're in China, or if you're in Russia, you're in the South Pole, you're in the North Pole. These levels can change, and sometimes you get intervals because depending on where you are, there might be different concentrations of isotopes. And now let's look at carbon, for example. Carbon has 6 protons. The average atomic mass is 12. So that tells us most of these elements where Z is 6, A will be 12. That means that carbon has 6 protons and typically 6 neutrons. Because this is slightly over 12, sometimes maybe it has 7 neutrons, right? So that you might have different numbers in the neutrons that can change the mass. And here is the interval that's shown here. Now I'd like to spend a little bit more time discussing isotopes and what they can do. So most elements are mixtures of 2 or more stable isotopes. And we can look at, for each isotope, they have slightly different masses because they'll have different number of neutrons. But even with different masses, they're chemically identical. They have the same chemical properties, the same types of reactivities. Everything's the same besides their mass. And the relative proportions of different isotopes are essentially constant. So let's look at some of this a little bit more closely. So isotopes, again, distinguished by mass. So for example, there are 3 different isotopes of hydrogen, 4 different isotopes of iron. So it depends on the element and how it's formed during that fusion process, but you'll have more or less different types of isotopes for different elements. Obviously, the larger that element is, the more possibility that you can have differing amounts of nitrogen or of neutrons in there, differing amounts of neutrons associated with that element. Okay, so I want you to take a second here, grab a periodic table, and I want you to write down what's the atomic symbol for uranium-235. So look that up and write it out, and let me know what you got. The first thing to do is to find uranium. Now, if you're not super familiar with the periodic table, it might take you some time. You could use a web app that helps you kind of scan through and identify those. But the more you use the periodic table, the more that you will be able to find, or the more quickly you'll be able to find these elements. So I would practice looking at these, and again, during timed quizzes or exams, it's going to be helpful to be able to identify these more quickly. Uranium is going to have the 92 protons. So that is its atomic number. That identifies what the element is. So the other thing you'll notice when you look at it on the periodic table, it's uppercase U is its atomic symbol. And then we know that the Z term is going to be 92 for here. And now we have to figure out what is happening in terms of the other value on the top, and that we already were given that information. It's 235. So if I want to determine then how many neutrons are in there, I would take that 235, subtract the 92. This is kind of nice, right? Because it is, we kind of have that already created here. And that's maybe a good way to remember that it's kind of like setting up a subtraction problem. Then we can have 143 neutrons. So I didn't ask you for that information necessarily. I really asked you for this information. But it's kind of a helpful reminder that, oh, if I set up this subtraction and I complete that arithmetic, then I can identify how many neutrons are there. So we know these are protons, and the neutrons are once we've solved that problem. Isotopes can be used in different types of sciences, and one that you might be familiar with or have heard about is sometimes these will be used in pharmacy. So in order to understand the biodistribution of biopharmaceutical compounds, frequently technetium is made up as a man-made radioisotope, and it's attached to a pharmaceutical compound, and that is taken in by, through a pill, for example, or a beverage, and then that compound's metabolized by the liver, and then it goes into specific organs, such as the heart or the bones or the liver, and then in a normal organ, for example, the uptake of this radiopharmaceutical compound will have certain characteristics of uptake, clearance, and distribution. And then maybe organs which are not properly functioning, for example, there'll be abnormal signals then once we look at the scan that can pick up that radiopharmaceutical signal. So then you can have an indication of potential disease or potential organ malfunction. All right, another question just to see if you're paying attention. I want to know if you, for this atom, the lead, how many protons, how many neutrons, and how many electrons does this have? So your options are given here, and you can identify which of those is correct and then submit your answer. So another learning check that I'd like you to do, I'd like you to look at iodine 131, bromine 81, and then also copper 65. So I'd like you to do some math, figure out how many protons, neutrons, and electrons are found in those elements, and then post your response. Now that you have a better feeling for what makes up an atom and the protons and the neutrons and the electrons and how they're related to each other, now I want you to look at thinking about how, when we look at the periodic table, remember we have different masses on there, and how are those generated? So when we're looking at these, we are generally thinking about the elements looking at mixtures of isotopes. So an example of hydrogen, we have an isotope of this 1 proton and no neutrons, and then this hydrogen we have 1 proton and 1 neutron. If we have the mass, and now of course in a perfect world the atomic mass units would equal exactly 1. The problem is this wasn't, when at that time when we defined the exact atomic mass unit, there was differences in the accuracy and the precision of the instruments that were used at that time. So now that instruments have become more accurate and precise, that initial unit is slightly off of what we would have predicted or developed. But the abundance of isotopes with no neutrons with hydrogen, 99.985% of those have no neutrons. However, if we're looking at with 1 proton and 1 neutron, which has this atomic mass of around 2, the percent abundance is approximately 0.015%. So hardly any of them. So how do we define atomic masses? Again, it's the average of the masses of all the stable isotopes of a given element. And we calculate them by looking at the weighted average of these. And we use the atomic abundance, like this number, these values, to do that. So let's look at some more examples of this. If we're looking at hydrogen, so if we get the averages, we basically take this mass number and multiply it by the percentage, the abundance, right? So this is a percentage. So to get a percentage, usually divide by 100, multiply by, to get a percentage, usually multiply by 100. Here we're going to divide that and make it a decimal point, right? So we have 0.99985, which is 99.985%, the same thing, but we make it a decimal. That gives us if we multiply these, that gives us the weighted average, and then this is 2 times 0.00015, and that's the weighted average that contributes to that compound. So then we add those together. This is rounded up from this value, and that's how we determine the weighted average of those compounds. And so you can kind of see here too, the isotopes are shown in this interval, and it's associated with various amounts of neutron mass depending on where you might be on different locations on Earth. So different concentrations in different locations. So when we go back to the discussion with the John Dalton and his theory that postulated that in any sample of a pure element, all of the atoms are identical in mass and other properties. Well, they're identical in chemical properties, but isotopes, what we know about isotopes, says that this initial hypothesis was actually incorrect. And that's fine to have an incorrect hypothesis. It allowed us to create experiments that tried to look more closely at that, and now we've found out and identified neutrons are important in changing the mass. So I just wanted to show you a couple of different kind of fun tools for looking at this idea of atomic composition, atomic number, different isotopes. So what we can do here is in this, and I'll link this, or you'll be able to find this in this video. But we have the nucleus. If I put a proton in here, it tells me which element it is, right? So every different number of nuclei or protons I put into the nucleus as I add protons, or I can take them back out. I don't think I can. Oh, I can delete them by clicking on them. So I can add another few in here. I can just keep getting bigger and bigger elements. So 6, right? So that's the atomic number. That is the mass at this current time. And so this example would be a really short-lived isotope, isn't readily available by ordinary means, because normally we'd have a certain number of neutrons in here. And so these are all until I still have 3. It still says this below. 4. Oh, okay. So now this is a radioisotope with a half-life of 19 seconds. So not very long-lived, but maybe with this atomic mass units of 10, it's something that does probably exist at least for a short amount of time, or can. Okay, now we added another one of those, right? So it went from 19 seconds to 20 seconds. Okay, so these are getting to be more stable, and we're going to add another one. Okay, so 98.89% of all naturally occurring carbon is this stable isotope. Great. Okay, so this is about more what we'd expect. So let's add another one here. Let's see what happens. Okay, so now that drops to 1%. So now we get 13. So we have 1, 2, 3, 4, 5, 6, 7 neutrons, and then this becomes a very small percentage of that. Let's throw out one more and see what happens here. All right, radioisotope with a half-life of 5,730 years. So this is heavily used for determining the age of various materials. So if we can look at how many C14 elements are in a compound, you've heard of carbon dating, for example. The number of these elements within a sample gives us an idea of maybe how old that sample is, because we know the half-life, and it can help us date that. Let's throw in one more for good measure. Okay, so now we're getting to half-lives of really short amounts of time, and these start to become less stable or just not viable. So we keep adding these. C17, very ultra short-lived. So we really don't see that or use that. So it's kind of an interesting little tool that we can look at various different elements like this. We can, go to nitrogen, for example, and do the same thing and kind of have something, get a better idea of what types of compounds are out there and different types of isotopes. Another fun interactive tool that I'll link here is that you can have a better understanding of what it means to have that percent average that I was just talking about in the lecture slides. So we can change the sliders if we have, depending on the number of isotopes within this compound. So this is if we're looking at the atomic mass unit, is the average is 25. So magnesium has the atomic number of 12. So it always has 12 protons in it. But we're going to look at adjust the number if we have 12 neutrons or 13 or 14, for example. That's the Mg 24, 25, 26. Tells us the different amount of neutrons. And we're going to change the percentage. So this is the typical relative abundance of each type of these magnesium isotopes. But I'm going to change this, right? So then we're going to change the relative abundance, and we're going to say, okay, we're going to reduce the number of these, with the 12 protons and 12 neutrons. We're going to change how many atoms within our group of 100. And that's essentially what we're doing with weighted average. We're just saying this number gets really tiny as this gets down to like a 1%. Right? You only have 1 in 100. If it's point something percent, right, you'd have, you'd have to go out to maybe 1,000 atoms to see a few of those red ones in there. So this tells us this is the atomic weight, the average weight. If this were what the relative abundance were in real life, this is what the average atomic weight would be based off of percentage. And remember, it's just multiplying that percentage by the actual weight, and then we average. So we get that value over here, and then we add those all up and average them out. So we can have, for example, if I just say, there are Basically, none of these, none of these, none of these, then the average would be 25. If I say that all of them are here, the average is 24. If it's all here, the average is 26. So it just depends on where you're putting these. If we get these all to, 50, or actually it would be closer to, 33 elements, then we should have the average be closer to the 25, right? So this gives us about an even distribution. You can kind of play around with this, but you can see if we're going to increase the number of the magnesium 26 elements, then this value is going to go up after you get a certain amount. If we increase the number of those, we can change those values around. So this is just kind of a fun interactive way. But really when we're doing the weighted average, we're just kind of looking at based off of 100, right? That's why we're multiplying it. We take that percentage. It would be like 0.32, 0.35, 0.31. We multiply those values by the weight. Then we get the values over here, and then we take the average, and that'll come out to this average weight. So that's the idea of the average atomic weight. So another interesting thing that we can look at with different isotopes within compounds is, so this is kind of interesting, crime scene investigation. There's this case study that talks about there was a murder scene, and then it's looking at the sugar in the coffee, and it happened to be cane sugar instead of beet sugar. And the beet sugar is more common in the United States, and cane sugar is a lot more rare nowadays. So you might be surprised, most of our sugar comes from beets in the United States. So this can help determine clues about things, for example, where sugar comes from. And the ratio of carbon-13 to carbon-12 is distinguishable between cane sugar and beet sugar, and it has to do with how those elements take in carbon dioxide through a C3 or C4 pathway, which is essentially it adds that carbon dioxide, that carbon, into a chain on a 3-carbon group of molecule versus a 4-carbon group. But that'll change the isotope that's involved as well. So it's something to look at, something that can be interesting, something you can do to identify where different things are from and the origins of certain compounds you might see in food or in other chemicals. So I did mention this earlier, but I did also want to come back and reflect on this idea of carbon dating, just talk to you a little bit more about this and how it generally works. So one of the big things that happens is you can generate some of these different isotopes through cosmic radiation. So radiation from the sun or from outer space. Essentially, you have high energy beams of energy coming in, and we have a very plentiful layer of nitrogen in our atmosphere. And when that energy hits the nitrogen, we know that nitrogen actually has one more proton than carbon, but it can flip that energy can change a proton to a neutron. It's kind of interesting. So it'll actually adjust that compound, but it'll have the same mass. So we have nitrogen 14 and carbon 14. So these are the same masses, but that energy, what it did is it actually changed kind of the spin, and it changed the properties of that neutron, and it changed it into it changed the proton from a proton to a neutron. It eliminated that electrical charge. So then we have a carbon-14 element. What also happened in this cosmic radiation process, one of the electrons will have left. So this will still be a neutral compound, but it's going to be heavy carbon, carbon-14. And this is the carbon we talked about before. It has a very long half-life, approximately 5,000 years. So what happens is this carbon in the atmosphere can bind with oxygen to form carbon dioxide. And we just talked about those different cycles within plants, the sugarcane versus the beet. That'll take on that carbon dioxide in the plant material, and that will have different, depending on how quickly this happens or how it happens, that plant will take on more carbon-14 or less carbon-14 based off of that cycle of how it works. Then we have plants or different animals will come and eat the plants, and that will take up a certain amount of carbon. That animal at some point, and that carbon will get integrated into antlers, into the tissues, into the muscles and bones. Typically, if we're looking at this long term, right, the bones are the only thing that's left. But the carbons within that bone will have different amounts of C14. And the half-life, basically what that does, after a certain amount of time, that what we say when we mean half-life is this will decay back into nitrogen-14. So some of that energy that came in here will be released, and that will turn from carbon-14 back to nitrogen-14. And then you can take the sample of this bone, for example, and over time, right, at death, these are all going to be filled up with carbon-14. 5,000 years after death, half the half-life, half of them are decayed, and so only half of those will be remained as the carbon-14. Another 11,000 years from death, then we have another half gone, half of the starting point, obviously, and the same thing. So for every 5,000 years, you'd have 5,000 left. So the half-life gives us the amount, the percentage of that carbon-14 left in that animal, gives us an indication of how old it is. So that's kind of how the carbon dating works. There are other than carbon dating, you can use uranium dating. The error margin for the dates in rocks can be as low as less than 2 million years in a 2.5 billion year time frame. There are different types of radiolabing. Carbon dating is good for certain things, but maybe for some of the things that are on a geological scale, we might use different elements to study decay and look at half-lives to figure out how old things are. So that's the basis for carbon dating and how that is used in science to understand how old certain artifacts are or certain geological structures might be. That's the end of this section on the periodic table and understanding the difference between different types of isotopes and how they're used in science.